I'm going to try and persuade you that I know something about artificial intelligence. You may laugh, but I believe I have some credibility. Anyway, you will judge that after you hear what I have to say. In 1984, which of course makes me quite old now, I developed what I called an inferencing spreadsheet. Well, 1984 was a long time ago. It was before the IBM PC, for example. The Apple Macintosh computer was only just emerging. Spreadsheet programs were hardly around at that time. It was only during the early 1980s that word processor applications had emerged. My own computer, which was not an Apple, not a PC, but it worked on something called the S100 bus, and it had an enormous, 15 megabyte hard disk that kept the office warm. Nevertheless, I had the idea of creating a user interface to a matrix, that is to say, something with rows and columns, and that you would put into the rows different instances of something. It could be different people, it could be different religions, it could be different animals, anything you like. And then across the top in the columns, you would have the attributes that tended to describe that domain of objects, whatever it was. So if it was animals, it might be whether they were domestic or farm animals, where you might find them, what they might eat, that sort of thing. And then in the body of the spreadsheet, in the cells, you would have the attribute values that were relevant to any particular animal. And as you read across a row from, say, cow, you'd have a column for, say, likely disease with an entry for, say, foot and mouth. So you'd have instances that I called elements or cases, and you would have the attributes of that set of cases, and you would have the attribute values that would vary depending on the case in question. Now, that's not particularly remarkable. What was interesting was that you could leave missing values in this spreadsheet. So you would complete it maybe 60%, 70%, 80% with whatever information that you had, but some of the cells would be left empty because you didn't know their values. And then you could press a key on the keyboard and it would do an inference as to what that value was likely to be. And what's notable is the way in which it did that inference. I was deeply into Daniel Kahneman at the time. He wrote a book called Judgment Under Uncertainty and Bias. I was also into a book called Categories and Concepts by Smith and Medin. And I'd already had quite a lot of experience in programming something called repertory grid technique, which would locate elements in a multi-dimensional space. So, you'd have people and a set of dimensions, and you'd rate those people on those dimensions, how intelligent they were, how tall they were, how attractive they were, whatever you wanted. I already had quite a lot of knowledge about multi-dimensional techniques. When I started on categories and concepts, it was with a view to understanding how people would infer categories that objects fell in from the limited information that they had. Let's say you go to a party and you meet somebody and they say that they are an investment analyst, a street cleaner, or whatever. You may infer quite a lot of information just from this one tiny unit of knowledge that you have about them. Now, at the time, people were using symbolic approaches to artificial intelligence. They were building things called expert systems, rule-based expert systems, where you would try and capture expertise in a set of rules. And indeed, I worked on these systems from about 1984-85 onwards, when I worked for a company called Logica in Cambridge. There was a lot of work going on in expert systems and human-computer interaction there at the time. And in a way, unfortunately, what happened was that logical approaches, symbolic approaches to artificial intelligence tended to dominate.
There wasn't much interest in these probabilistic approaches that I was working on.
So I experimented with several algorithms for making the inferences. One fairly straightforward algorithm is, in the instance, the case, the example that you're trying to make an inference about, you match that example with all the other examples that you know about, and you get some kind of matching score or a rank of the degree of matching. And then you have a look at the kinds of values that the top ranking cases have on the attribute value that you're trying to infer. And that kind of algorithm worked extremely well. And in fact, when I packaged up this technique and had an arrangement with a company called Elsevier Biosoft, Elsevier, the scientific publisher that had a branch in Cambridge called Biosoft at the time, and we packaged this up into a product called Expert 4. And indeed, the Home Office trialled the use of this product in making inferences about the time of death in cases where they found bodies and they needed to establish the facts surrounding the case. So they had, hundreds of instances of corpses that they had found and the results from blood tests and various other measures. And in the cases that they knew, the time of death. And so this program was able to make inferences about time of death from the surrounding information.
If you happen to be familiar with large language models, then you may notice a certain similarity
with word embedding here, because you could have had words as all the examples, you could have had attributes of words, you could have had attribute values for those words, whether they were nouns or verbs or whatever. So that would have been one approach to doing it that would capture human knowledge about language and vocabulary, and that could indeed have been and could still be a shortcut to the development of artificial intelligence generative language models. In the event, what seems to have succeeded as word embedding was to place each word in the multidimensional space of other words, more or less the same kind of ideas that I'd been working on since, perhaps before even 1980. So there, in a sense, is my claim to have an understanding of the current generation of large language models and what's going on in artificial intelligence. Indeed, I can remember throughout the years having many arguments with people about the use of probabilistic logic and the kinds of approaches I was talking about, as opposed to the kind of deductive logic that was being used in symbolic approaches to artificial intelligence. While I was working at Logica, we were all put on the track of the symbolic approach. So I spent many years working on that. And unfortunately, it was to the detriment of me pursuing my own ideas. Those ideas could have, in a way, led more quickly to where we are with large language models now. But then, of course, that's purely hypothetical and counterfactual, and so you make of that what you will. Anyway, I have tracked artificial intelligence throughout the rest of my career, even though I've done many other things in IT management and in human-computer interaction especially. I wrote a paper once called "The Role of Games and Cognitive Models in the Design of Complex Dynamic Systems." And I kind of like to think that that's been my central interest, shall we say, because the opportunity to actually work in these areas has been somewhat limited, although perhaps I didn't pursue it as much as I could have. I developed my career along more of a line of least resistance. Well, here we are now in 2026. That's not really very far away from 2029. 2029 was Ray Kurzweil's prediction about when we would achieve artificial intelligence at human levels. Really, that seems to be very much on track. Ray Kurzweil arrived at that prediction through an analogy with Moore's law. Moore's law being the law that said that computer processing power would double every year or two. And indeed, it did do that up till relatively recently. So he extrapolated from that, if you like, what would happen to artificial intelligence or the capability of computers to support artificial intelligence, and came up with the date of 2029 for artificial intelligence rivaling human intelligence. And of course, Ray Kurzweil is also famous for having coined the term in the computer sense, the singularity. There's another sense of the singularity in terms of black holes, but in the computer sense, the singularity is when artificial intelligence is sufficiently good that it can create itself, it can supplement its own capability, and then you have the possibility of a runaway situation where it very rapidly or quite rapidly becomes super intelligent. So now in 2026, the artificial intelligence world is dominated by large language models. While that's not a bad thing, one needs to remember that there's a lot of other artificial intelligence work going on, and it's just important not to forget that. Although some of the principles behind large language models, in particular their generative or predictive ability, can be used across a very wide range of tasks. So, for example, and this is a little bit frightening in a way, every company that you've interacted with on the internet has been collecting data about you. Some programs are collecting every keystroke, mouse move, and mouse click. Well, now think of those behaviors as being the equivalent of words in a large language model. Now, if you feed the model a sequence of behaviors up to a certain point and ask it to predict the next behavior, then you've got pretty well the same as has been used for large language models. In other words, we have the technique already established for behavioral prediction. And these are the very techniques used in agentic AI and robotics. So on the one hand, we have architectures that have been used in large language models being turned towards other tasks, in particular behavioral prediction. And on the other hand, we've got other types of artificial intelligence systems that are being used in other domains. And we still have a whole tranche of work in symbolic AI. Okay, well, let's wrap up on this. I'm going to produce a series of videos about artificial intelligence. In particular, what I'm trying to do is promote my book, Good Manners for Robots. So why Good Manners for Robots? The essence of it is understanding what good manners are and being able to train artificial intelligence systems to understand and to work within the parameters of good manners is one way forward to addressing the alignment problem, that is to say, aligning human values with the values of artificial intelligence. I should really explain where I'm coming from with all this. My background is in psychology, economics, social sciences generally, but I've worked in the IT industry for 30, 40 years. So my approach is something of a merger of the two. Indeed, I worked in the area of human-computer interaction for many years and built up a team of perhaps 20, 30 people who were distributed around the world, training others in the development of more useful and usable user interfaces to software systems. From an academic point of view, I've always been somewhere between psychology and economics, and indeed, having studied Daniel Kahneman since the 1980s, I regard myself as a behavioral economist when talking about economics. When talking about computing, I regard myself as an expert in socio-technical systems, that is to say, the design of systems that fit into some sort of social context, not just the user interface, the UX, the human-computer interaction element, but a wider social context. So when I come at artificial intelligence now, My strength, if you like, is to compare human cognition and what is going on in artificial intelligence. So clearly, a lot of AI people are doing exactly that in their attempt to achieve artificial general intelligence. Although it's not necessarily the case that a general intelligence has to be a human intelligence. There's a lot to learn by this comparison of computer artificial intelligence and human intelligence, because in fact they are very different things, and many academics have found that you can learn a lot from the other discipline. What I find interesting is taming, in a way, the enthusiasm for artificial intelligence systems by demonstrating their differences with the human system, but also looking at the similarities. The main distinction, in my view, is that human intelligence is embodied. That is to say, we have our own human bodies, and that biological, physiological, emotional basis for our human intelligence, which tends to drive our intelligence far more than our rational processes, is fundamental to the way that we think about things, and is in many ways quite different from the way that artificial intelligence is processing its information. In fact, I have a whole approach to this which I call the human operating system. If you use this analogy of an operating system and apply it to people, it gives you a perspective of understanding in more or less the same sort of language as you use in computing, and facilitates comparison between the human operating system and the computer operating system. During my degree in psychology, back in 1972-73, one of the only courses that I really related to was something called individual differences. And that's where I first came across Kelly's personal construct theory that he had developed and documented in 1955. Personal construct theory had a technique associated with it called repertory grid technique. In repertory grid technique, you list a number of things in a particular domain. It could be people, it could be cars, it could be anything. And then one of the ways of doing it is you take 3 of those at the time and ask, what is the odd one out? When you've established the odd one out, you work out, well, what's the basis on which you're making that decision? And you call that a dimension. So eventually you end up with a list of objects, elements, cases, whatever, and a list of dimensions on which you can rate all these cases. And then if you go on to rate each case on each of the dimensions, and then subject that to computer analysis, you've completed everything that's required for what's called multidimensional scaling. And in multidimensional scaling, you can, for example, look at the distance between 2 things in your space. If it's 2 people, how close are they in this multidimensional space, or how far apart are they? And this seems to relate very much to the way that people make judgments. So, for example, if I tell you somebody is a politician, then from just that one fragment of information, you infer an awful lot about them. You might be able to infer their characteristics on, 10 other dimensions. You may be right, you may be wrong. Your stereotypical understanding of what a politician is will slot in and automatically make you infer all kinds of other characteristics about them. These other characteristics sort of come to the fore in your mind. They raise in prominence. And this is an effect which in psychology you call priming. Now, this kind of way of making inferences is quite different from the logical or reasoned approach, which is, of course, the approach that artificial intelligence took for many years. And indeed, I would argue that that's why that approach didn't work. Human cognition is just not like that. The system I developed in 1984, called Expert 4, now in retrospect can be seen as a sort of halfway house between symbolic approaches and machine learning, neural net kind of approaches. It's a halfway house in the sense that when you complete a table of rows and columns, elements in the rows, attributes in the columns, attribute values in the body of the spreadsheet, you're using what's already known about those elements. You've defined a particular class of attributes that are relevant to them. You've defined a particular set of attribute values that works with those attributes. So you put quite a lot of human intelligence already into the process. And then instead of using that to make deductive type inferences, you use it to make the sort of probabilistic inferences that are characteristic of the way people make inferences. There's also a sense in which large language models are a halfway house because, of course, the training sets for large language models, enormous corpuses of text harvested from the internet, already encapsulate a lot of human knowledge. It's in the statistical patterns of that text that human knowledge has been captured. What large language models do is extrapolate, if you like, from that knowledge. So one thing that makes large language models intelligent is what's already encapsulated in the training set. And that training set has been created, or at least up to now, largely by humans. When the training set starts to be synthetic data that has been created by artificial intelligence itself, that may work, but we're also into the prospect of something called model collapse, where one set of training generating output that then is used as a second set of training that creates output that's used for a third set of training eventually seems to converge on gibberish rather than any higher insight. Well, whether that failing in large language models can be mitigated by some technique or another remains to be seen. So, of course, the advantage of using human text and the intelligence that's contained within that is that the intelligence is already in there. It doesn't have to be created from scratch. And in the same way, the kind of spreadsheet or table or matrix models that I was creating with Expert 4 are also a kind of halfway house. They capture human knowledge, and then that can be processed to generate inferences. The thing is about the Expert 4 approach is that it's not just capturing the knowledge, it's structuring it to a degree. It's structuring it in its attributes and attribute values of the cases in question. Now, that structuring that's done by humans may actually turn out to be extremely valuable and a lot cheaper than the process that subsequently has to be done by an artificial intelligence system. So there is the possibility that some of these other techniques of capturing and training information for artificial intelligence systems may turn out to be cheaper in the long run. They are a kind of hybrid that might actually be more efficient from a data capture point of view, as indeed is all the information that's contained in data sets.